Deep in space, the James Webb Space Telescope lives up to its promise. From unexplainably bright galaxies to the possibility of finding life on exoplanets to challenging our understanding of the beginnings of the universe, this powerful telescope has astounded the scientific community. It has given us incredible ideas, including many structures that should not exist. But here's the thing. The James Webb Space Telescope is turning everything upside down and making us realize that we may need to rewrite the textbooks on the origins of the universe. To understand this dilemma, let's take a quick look at the Big Bang, the most well-supported theory of the origin of the universe. The Big Bang was originally a simple idea derived from three interconnected facts and Einstein's general theory of relativity. According to the theory of relativity, a universe with uniformly distributed matter and energy cannot remain stable in a static configuration. The spatial structure of such a universe must either contract or expand. From an observational perspective, the sky beyond the Milky Way is spiral and elliptical. Their distances can be measured, and the light from spirals and ellipses is shown by a redshift. More distant objects have a greater redshift in direct proportion to their distance, consistent with the expanding universe. Taking all this together, we can conclude that if the universe is expanding today, it must have been smaller and denser in the past. The first person to put this information together was Georges Lemaitre in 1927. Others, including Howard Robertson in 1928, Edwin Hubble in 1929, and later Arthur Walker, came to the same conclusion. Over time, additional implications of the Big Bang emerged, including the idea that the universe was initially hotter and denser. As the universe expanded, it cooled, forming neutral atoms that eventually gave rise to stars, galaxies, and cosmic structures. But this understanding of the Big Bang isn't all there is to it. Three additional ingredients have been discovered. Dark matter, which is clumpy and gravitational but doesn't collide with ordinary matter or photons. Dark energy, which acts like energy inherent in the universe itself. And cosmic inflation, which limits how far back in time we can estimate the hot Big Bang. These ingredients allow us to describe the state of the universe at the beginning of the Big Bang, including its temperature and density. But despite the observational evidence supporting this model, it may not be entirely accurate. Whenever we observe the universe in a new way, we need to check whether what we see is consistent with this model. This is where the James Webb Space Telescope has played a key role. Its observations of the early universe have raised doubts about current cosmological models, suggesting that our understanding of the Big Bang may need to be revised. The James Webb Space Telescope is more advanced than any other NASA instrument. As James Webb senior research scientist Matt Greenhouse notes, this instrument has given humanity its first high-precision view of the infrared universe. Thanks to its capabilities, we have been able to discover and characterize galaxies from the earliest stages of cosmic history. Before James Webb, there was only one galaxy, GNZ 11, identified about 400 million years after the Big Bang. Now, more than 100 candidates for early-age galaxies have been identified, and several of them have been confirmed. These early galaxies have mysterious properties. They appear to be massive, bright, rich in heavy elements, and actively forming stars, a property that challenges current theoretical models of galaxy evolution. There are limits to how quickly matter can accrete on these objects, and while these limits can be temporarily overcome under some conditions, they should not persist for long periods of time. James Webb's discovery caused quite a stir, and some have questioned our understanding of how galaxies form and evolve. In addition to galaxies that are inexplicably large, James Webb also discovered a massive black hole in the early universe. The first quasar discovered by telescope, J119, has a mass 10 million times that of our Sun and existed only 570 million years after the Big Bang. In April 2023, the telescope broke its own record by detecting a black hole in the galaxy GN-Z11, 13.4 billion light-years away. The black hole is about 6 million times the mass of the Sun, challenging current theories about how such a massive object could have formed so early. In addition to this groundbreaking discovery, James Webb has discovered thousands of galaxies similar to the Milky Way that are much more common in the early universe than previously thought. These thin spiral galaxies should not have existed during the era when galactic mergers were dominant. The discovery deepens the mystery of how galaxies and life first emerged in the universe. Webb's observations have also revealed completely new and unexplained objects. For example, he discovered a pair of Jupiter-mass objects in the Orion Nebula that are too small to be stars but unlikely to be planets. These discoveries could point to new mechanisms for the formation of planets or stars. Closer to home, telescopes have revolutionized our understanding of Saturn's rings, revealing that they are much younger than previously thought and taking detailed images of the weather systems of Uranus and Mars. The James Webb Space Telescope's ability to study distant planets, especially exoplanets, has profound implications for our understanding of planetary formation and the potential for life beyond Earth. Exoplanets are planets orbiting stars outside our solar system, and studying them offers a unique opportunity to learn about planetary systems that may be very different from our own. Before the advent of telescopes like the James Webb, scientists could only guess at the conditions of distant worlds. Now, with its powerful infrared capabilities, the JWST is providing scientists with concrete data that will allow them to peer into the atmospheres of these planets and reveal details that were previously impossible. One of the most exciting advances in exoplanet research is the James Webb Space Telescope's ability to detect chemicals in the atmospheres of distant worlds. These chemicals can provide important information about the planet's condition, such as its temperature, composition, and potential habitability. Most importantly, the telescope detected key signs of life, or biosignatures, in the form of carbon-containing molecules and methane. These molecules are considered the building blocks of life as we know it, and their presence in the atmosphere of an exoplanet suggests that the conditions necessary for life may exist elsewhere in the universe. A particularly notable example is the discovery of carbon-containing molecules and methane on the exoplanet K2-18b, which is about 120 light-years from Earth. K2-18b is classified as a mini-Neptune, meaning that it is a gas giant smaller than Neptune but still much larger than Earth. The planet is located in the habitable zone of its star, the region around which conditions are suitable for the existence of liquid water. The discovery of methane in the atmosphere of K2-18b is particularly interesting because on Earth, methane is produced by biological processes. This does not necessarily mean that K2-18b harbors life, but it does raise the tantalizing possibility that the planet could have conditions suitable for life. The presence of methane on K2-18b has generated considerable interest in the scientific community. On Earth, methane is primarily produced by living organisms, particularly microorganisms. Methane can also be produced by abiotic processes, such as volcanism, but the discovery of methane combined with other molecules, such as carbon dioxide and water vapor, strengthens the hypothesis that K2-18b could have a habitable environment. In fact, some scientists have suggested that K2-18b's thick atmosphere may contain liquid water, making the planet even more likely to harbor life. The significance of detecting biosignatures like methane and carbon-containing molecules on exoplanets like K2-18b goes beyond finding extraterrestrial life. These discoveries also provide valuable information about the planet's formation and evolution. By studying an exoplanet's atmosphere, scientists can learn about the various stages of a planet's development, from the accumulation of gas and dust in the early stages of planet formation to the chemical reactions that occur as the planet evolves. This knowledge can be applied to our understanding of how planets, including Earth, formed and evolved over billions of years. In addition to providing clues about planetary formation, studying the atmospheres of exoplanets can help scientists understand the diversity of planetary systems in the universe. The discovery of exoplanets with atmospheres rich in methane and other carbon-containing molecules suggests that conditions that could support life may not be as rare as we once thought. In fact, it is becoming increasingly clear that there may be many planets in the universe that have the potential to support life. The James Webb Space Telescope is uniquely equipped to explore this possibility thanks to its ability to detect and analyze the faint light emitted by distant exoplanets. By studying the light passing through these planets' atmospheres, the telescope can determine the composition of the gases present, providing important information about the planet's environment. In addition to K2-18b, the James Webb Space Telescope has detected potential biosignatures in the atmospheres of several other exoplanets. In some cases, the telescope has also found evidence of water vapor, another essential component of life. The discovery of water vapor in the atmosphere of a planet in the habitable zone of a star is particularly interesting because it suggests that the planet may have the right conditions for liquid water to exist on its surface. This, in turn, raises the possibility that the planet could support life in the form of microbes and more complex organisms. The discovery of carbon-containing molecules, methane, and water vapor in the atmospheres of exoplanets is a major step forward in the search for life beyond Earth. These results do not provide definitive evidence for extraterrestrial life, but they do suggest that the conditions necessary for life may be more common throughout the universe than previously thought. The James Webb Space Telescope has not only transformed our understanding of the universe, but has also opened a new era in the search for life on other planets. Its discoveries have challenged our preconceptions about the origins of the universe and the potential for life beyond our solar system. The telescope has shown us that the universe is far more diverse and complex than we ever imagined, and its findings will undoubtedly shape the course of astronomy and astrophysics for years to come.